Hey everybody, my name is Alex. I'm a master's student in business analytics, and today I'm going over part two of our two-part NBA data analysis project. If you haven't seen part one yet, I will link to that in the description. In part one, we scraped our data off nba.com/stats, and we're going to be using that data today in part two for analysis. So again, if you haven't seen that video yet, go ahead and pause this video now and go to that web scraping video, part one. Link to that in the description. If you just want to be able to follow along today, I also have this Excel file, which is the data that I scraped, posted on my GitHub. That is also going to be linked in the description, so you can go ahead and check that out too, so you can follow along here in part two. So without further ado, let's get going. So we have our bringing in our pandas package, because what would we do without it? Plotly is my personal preference for data visualization in Python. And then this argument here is just so we can see all of our columns in a wide data frame. So here we are defining our data frame. This is the data that we scraped, and we're just going to call that data. So let's take a look at our data frame here. Sample 10 random records. Okay. So each row here, to understand our data frame, is these are total stats for one player in one NBA season, either the playoffs or the regular season. So this row here are the total stats for Boris Diaw in the 2012-13 playoffs. Let's see, we got Reggie Jackson, we got Lou Will, Mario Chalmers. Just thinking of a few in this data set. So in order to make it into this data set, you must have played in at least one game in the given season and season type. So if you are on an NBA roster and did not get in the game at all, that player will not make it into the data set. Just a quick caveat. So we have 10 years worth of data here. So dating back to 2012-13 and all the way through the most recently completed, as of now, NBA season, which is the 21-22 season. And then we have data for both the playoffs and the regular season. So let's go to look at the size of our data frame. So 7,293 rows and 29 columns worth of data. And now let's look at just the general kind of sections or questions I defined for our data analysis here in part two. And just a disclaimer, like these are just questions that I thought were interesting and looked into, but if you have any more ideas for anything you want me to look into, either in this data set or in some other data set, you can feel free to just let me know in the comments below, but these are going to be the three sections I'm going to be working on today. So first, which player stats are correlated with each other? Then how are minutes played and some other stats distributed? And then finally, just kind of on a broad macro level, how has the game changed over the past 10 years? And for these last two parts here, I also want to compare the regular season to the playoffs and see how the game is actually different. So again, if you have anything else, any other ideas for NBA stats you want me to cover, you can go ahead and put that in the comments and I will take a look at it. Okay, so let's get into our data cleaning. I don't think we have a whole lot of cleaning to do, but we can make our lives a little easier with a few lines of code here. Let's look at null values. And yeah, so no null values in the data set. That makes our lives easy. There are a few things we need to do. So let's first drop the columns we don't need. So this rank column here is just kind of an arbitrary sort column, basically. So in NBA, on nba.com/stats, you have the option to sort on a certain column. So in the context of our data frame here, this column is essentially meaningless. So we can go ahead and drop that. We're also going to drop efficiency here. You can look up the formula for that. It's pretty much like a sum of all the positive stats and subtracts out some negative ones. For the purpose of our analysis, not a whole lot of meaning, so we're going to go ahead and drop that as well. So data.drop columns equals rank and efficiency, and we'll make that in place. Okay, now I want to create a new column for the season start year here. So I want to be able to have a column that identifies the year in an integer form. So right now these are strings. So I want to pull out just these first four characters and turn those into integers. So you can say data year. And a couple ways to do this. You could make a list comprehension and use dot split. I'm going to use the series.str and then just want the first 4. So that'll give us what we want, but this is still an object, aka a string. We want this to be an integer. So we'll pass .s type int, and now we have integer. And we can go ahead and now define our new column. So we'll call this data and say season start year. All right. Now, I believe for the team here, I think in these past 10 years, New Orleans switched from the Hornets to the Pelicans. Let's see, just to make sure. Use that unique. And yeah, so New Orleans Pelicans, and here we have New Orleans Hornets. So there should be 30 NBA franchises. I think in this list, we're going to have 31. Yeah. So let's go ahead and standardize that. So say data team, and we'll use dot replace, and to replace equals, we'll pass a list here to capture both of those teams. So both NOP and NOH, and we'll change both of those to just one standard franchise name for New Orleans, and we want to make that change in place. Okay. And then lastly here, I just want to clean up our season type indicators. So this column, again, it's really just there so that we can differentiate between the playoffs and the regular season. I added this in when I scraped the data. So this regular season here is actually the literal string that was found in the API URL. But let's clean that up a little bit, just make this a little more user-friendly. So you can use dot replace again. So data season type dot replace, and we got to get that exact string here. Let's copy paste that in, and let's keep it simple. Just replace that with rs, and in place equals true. Okay, so I think we're good to go on data cleaning. Pretty simple there. But let's also pass through a couple lines of code here to make our analysis a little easier. So a little data prep. So I want to create 2 more data frames, one for the regular season and one for the playoffs. So we'll create a little filter here and say, so data where the season type is equal to rs. That looks good. And then we'll call this our rsdf. Then let's do the same thing for playoffs. Okay. And then lastly, if you go up here and look at our columns here, we have some columns that are totals columns and some of them that are ratios or percentages. So for example, if we have field goal attempts here, these are the total number of field goal attempts, whereas field goal percentage is a ratio of makes to attempts. So if we aggregated, did a group by, for example, which we're going to do, and took a sum of field goal percentage, that wouldn't make any sense logically. So we want to create a list of those columns that we're going to be using in our group by, and that'll save us some time later. So let's just call this list total calls, and let's get a look at our data columns here. And I'll go ahead and pick out which ones that I want, and then I can skip ahead until I have that ready to go. Okay, so we have all our columns here. Let's clean that up a little bit. So the only one I excluded here was games played, just because we're not going to be using that in a group by at all. So other than that, these are all the columns that we can take a sum of. So let's run that. And now we can move on to section 1 of our data analysis. So let's look at player stat correlations. The way we can do that is just with a simple dot core. And this gives us our correlation metrics. The reason we don't want to do this yet, though, is because this is going to be of total stats. So if you look at something like, say, 3-point shots made, and something like rebounding. So it's, pretty strongly positively correlated. But the issue here is that since these are totals, the more a player plays, he's naturally going to accumulate more stats. So it's not really a fair representation of kind of these player tendencies in terms of what they frequently do well and what they frequently do not quite as well. So we're going to want to take a look at this on more of like a per minute played basis. It'll be a better representation of correlations. So first, rather than separating out our playoffs and regular season, let's group by these total stats for each player in any given season. Because also we want to get rid of those small sample sizes here. And the playoffs could potentially be small sample sizes, which could throw off our per minute ratios. So let's say data dot group by, and we want to group by the player, as well as the player ID, just in case we have players who have the same name. And then we want to group by the year. And then we'll take the sum of our total calls, which we just defined up here. So total calls dot sum. And let's see what went wrong here. We need a list here. There we go. And then let's reset the index to pull these columns up, or these indices, I should say, up into the columns. All right, so we have our data frame, and now let's define this. So we'll call this data per min. Okay, and now I want to divide all of these stats by minutes played. So let's go ahead and do that. So we can say, use a for loop here. Say for call in data per min dot columns, and we want everything from index 0, 1, 2, 3, 4. I think, yeah, 0, 1, 2, 3, 4. So everything from 4 onward. And let's just overwrite these columns. So we'll say that the column is equal to the column divided by minutes played. And let's make sure that ran. Perfect. Okay. And then also in our group by here, we have to take our sums first. So that means we got rid of our ratios. So now let's go back in here and specify the ratios that we want. So we can bring back in our data per minute, say field goal percentage, and that equals field goal makes divided by field goal attempts, and so on. And I'll skip ahead until I have all these ratios filled in, and then I'll walk you through them. Okay, so I have all my ratios. These are just shooting percentages. This is going to be percentage of attempts that are 3-pointers. This is a measure of shooting efficiency, so average points per attempt, and then percentage of field goal makes that come from behind the arc. And then we have our free throw rate, which is free throw attempts per field goal attempt. True shooting percentage here, this is a more modern measure of shooting efficiency that's going to take into account not just your shooting percentage, but it's going to give more weight to 3-pointers and also take in your free throw percentage as well over here. It's not actually a percentage. I think that it doesn't, the calculation here doesn't actually have a unit, but this is the formula here, and you can look this up to learn a little bit more about that. And then it's just a turnover ratio. So let's run that. Make sure we have all of our ratios. That all looks good. And then the next thing I want to do here is I want to filter out players who barely played at all so that they're not messing up the ratios with a very small sample size. So I come down here, let's decide, let's put a minimum number of minutes required to play to make it into our data here. Oops, we want data per min. We still have our minutes column here. We didn't divide that yet or drop it. So let's say, let's find the percentage of players in this data set who played in at least, let's say, 100 minutes in any given full NBA season. So it's only like 88%, which is incredibly low, only 100 minutes and 82 plus games. But again, that kind of goes to show what we're going to see down here in our minutes distribution. Let's change this to 50. Okay, that looks a little bit better. So let's use 50 as our minimum here. So what we can do is come down here. Whoops, need to copy this. Data per minute equals data per minute or minutes is greater than or equal to 50. And we can rerun that. Then if we put this into our .core here, see we still have player ID here. So again, pandas can't differentiate between an integer column, which is actually categorical like player ID. So let's go ahead and drop that. So data per minute dot drop columns equals, we can leave in our total minutes column. Actually, we don't need to drop that. Say player ID and in place equals true. Essentially what pandas is doing here with this correlation matrix, it's taking all of your numerical columns and adding it in. So any categorical column will not make it into the .core matrix. But then again, it can't differentiate between these numerical columns that are actually technically categorical. So we can go ahead and drop those. And that looks good. So now what we can do here is we want to be able to easily see which of these correlations are particularly high, particularly low, or also possibly noteworthy, none at all. And the way we can do that is with a heat map. And this matrix kind of suits itself perfectly to that. So what we're going to use is Plotly Express here. And anything where I'm using Plotly, Plotly is great customizability, interactive functions, but the code can be a little tricky to memorize sometimes. So I highly recommend for anything with Plotly, go on their website and the code is all going to be right there. So let's go ahead and graph this. So we'll say fig equals px is Plotly Express. And here's the code for a heat map. And then let's just pull this in here. I think that should be our only argument. Then we'll go fig.show. And here's our heat map. So this is just the bar on the right, which is showing we have all the way from 1 down to -0.6. And don't mind this yellow line down the middle. Those are just stats that are obviously correlated with itself. So that is meaningless. But let's take a look at a few here that stand out. So remember we looked at rebounding and 3-pointers made. So let's see if we can take another look at that. So we have, so these are all going to be pretty negatively correlated with rebounding. So again, interesting. When you change it to a per minute basis, you find out that for the most part, players who rebound well are not going to shoot threes, make threes, or take threes at a high rate. So again, pretty negatively correlated here. So you can see these dark boxes that really stand out. Another interesting one here. So players who shoot a lot of threes, generally field goal percentage is going to be lower. That makes sense. That doesn't mean a whole lot. Let's look at player fouls here too. So total minutes of player fouls per minute negatively correlated. That makes sense. Field goal makes, yeah, interesting. So these are all going to be negatively correlated for the most part. Let's see if we get any with fouls that are positively correlated. So offensive rebounds, interesting. And same thing with defensive rebounds. So I guess it kind of goes to show most of the players who are committing a lot of fouls are probably big guys around the basket who are also grabbing a lot of rebounds. Negatively correlated with assists and player fouls. Let's check out steals, see what we find here. Not a whole lot strongly correlated. Negatively with rebounds a little bit. kind of interesting. There's not much correlation between player fouls per minute and steals. Let's look at assists here. So assists and field goal attempts, interesting. So I think what we're going to see here is, for the most part, there are a lot of ball dominant players in the NBA. So to have the ball in your hands, that's where you're going to have the opportunity to score, take shots, and get assists. So let's see our positive correlations here. So positively 3-point attempts, free throws, negatively correlated with rebounding again. So your guards who are handling the ball a lot, probably not grabbing as many rebounds. That has started to change a little bit, but this is over 10 years. So assists and steals, let's see. Let's look at points. So again, that's positively correlated too. So a lot, you have the ball dominant guys who are driving that correlation up. But you could go through this when you recreate this and kind of look at every single correlation here. A lot of interesting stuff. But for the sake of time, I'm going to move on to our next section here. So let's plot our distribution of minutes played. And I'm use Plotly again for this. So say fig equals Plotly express dot histogram. And our X is going to be, let's just start with our regular season DF and then minutes. And let's just say fig dot show. So if you think about this, this is going to be, let's see. So just number of players here. So we have 642 players total in the regular season who have played under 100 total minutes in that given season. So you can see that this is pretty skewed to the right here. It just goes to show most NBA players don't play very much. Like there are very few guys who are playing a ton of minutes in a given season. And again, this even doesn't even take into account guys who are on an NBA roster but never actually get into the game during a given season. So that maybe that's a guy like who just got called up from the G League, 10-day contract, or just got cut right away. So this number could really even be a little bit higher. Let's also pass in an argument to see the percentages rather than the count. So we can say his norm equals percent. Again, you can get all this code on Plotly's website. So yeah, it's crazy. 12.5% of players will not play at least 100 minutes in a given regular season. It's crazy. Let's see how this is different at all with, let's put in our playoffs DF. So pretty similar there. Just a smaller sample size with the playoffs. So what we want to do here to make it kind of a fair comparison is let's get our numbers on a per game basis here. So here's how we can do that. And I also want to be able to compare the playoffs and the regular season. And I want to be able to put it on the same graph here, so we don't have to toggle between our two data frames. So for this, we're going to use Plotly graph objects here. So we can say fig equals go for graph objects dot figure. And then we're going to add a couple traces here. So one trace for the playoffs, one for the regular season. So fig dot add trace. And we want go dot histogram, capital H this time. Plotly's, again, syntax can be kind of tricky. And then X is going to be equal to, see regular season first, RSDF minutes divided by RSDF games played. And then let's see what else we can do here. We can pull in that his norm argument also, make it a percentage so that we can kind of fairly compare playoffs and regular season, because otherwise they're just more, it's just a different sample size. So let's pull that in. Then I think we want to standardize our bin sizes too, so nothing's thrown off. So for that, we pull in our X bins here. So X bins equals, actually, let's print this out first before we, so that we know kind of what the max is. And we also need a name here so we can differentiate between our two histograms. So name here is going to be RS for regular season. Oops, let's copy this. We'll get it eventually. Okay. Need playoffs DF. Switch those out and change the name. Move this to the next line. And let's say fig dot show. I think we also, yeah, so right now we have these bars that are just next to each other. We want them to overlap here. So this is going to be another argument. And we'll pass through fig dot update layout. And we want the bar mode equal to overlay. And just so we can see both of our bars when they're overlapping, we'll make the opacity a little lower. So say fig dot update traces, and opacity equals set to 50% to pull that down a little bit. And now let's see what went wrong here. A problem somewhere. Let's see if we can find it. Here's why. Change that to playoffs. That should fix our problem. Okay, much better. Yeah, so here's why we want to change our bin sizes too, because right now we want these to be the same. So that's why these bar sizes are thrown off a little bit. So here's how we can do that. We're going to pass through our X bins, and this is going to be a dictionary. So we have start, and we'll set that equal to 0. Then the end, and that is, let's see our max here. This goes up to 46. So we'll keep that the same, 46. And then we want our bin size equal to, let's say 1. We can use 1 here. We can always go back and change this. And let's copy paste this down so it is standardized and run our code here. Okay, so very interesting stuff. So first, it's actually, we have our regular season distribution here is pretty normal. So a lot of guys getting the chance to play here, not really skewed left or right in any direction. Compared to the playoffs here, where you have a lot more guys on the tail ends of the distributions. So this is kind of proof to show that the roster, or the rotation, I should say, gets tighter in the playoffs. So more guys playing very few minutes, and also more guys playing a lot more minutes and not as much in the middle here. And one thing I want to do to see if this changes at all is I want to add in a minimum number of minutes and games played to even qualify here. Again, to just try to pull out some of these outliers. So let's define a function for that. So we don't have to type in just some long .loc. So let's define hist data. And we need a data frame. So default will be rsdf. We need a minimum number of minutes to meet. Set the default to 0, and then we want minimum games played, default also 0. And this, so we will call this, let's see, this will be df.loc. And then we want our 2 conditions here. So let's set that up. First one's going to be df min is greater than or equal to the minimum minutes argument. And then and here, the ampersand, df games played is greater than or equal to this part of the function. And then we only want the minutes column. And we want to divide that by games played. So everything is going to be the same here. We're just going to change the column for minutes to games played. And we can throw this onto a new line to make it a little more readable. Set that to GP. I think that should work. We'll find out in a second. So we can replace our input here with this data, and this is our RSDF. And let's set our minimum to set to 50, and then at least 5. We'll say games played to qualify. For the playoffs, I don't think we're going to need this as much because you're not going to have as many teams just trying out players in the regular season because these playoff games count, obviously. So, and then also it's a smaller sample size, so naturally these numbers are going to be lower. So let's say hist data playoffs DF, and then let's say 5 minutes and just 1 game. And we'll see what this looks like. Oops, and nothing happened. Let's see what went wrong. Got a return statement. That will do it. Okay. And okay, there's our distribution. So pretty similar. Looks like this kind of tail in the end is a little shorter, not much change for our regular season DF. But I'm kind of curious to see just how much is accounted for in this middle part of the distribution. So let's say we'll say from like 12 to 34. Let's look at our percentage for that. So we can call in our function here. So this greater than or equal to 12. And then we'll say and. This is less than or equal to 34. So kind of that middle part of the distribution. This should account for the vast majority of players, I would think, based on our graph. I'll put that in parentheses and say dot. It's about 75%, so that's pretty massive. 75%, and then let's compare that to those same bounds and look at our distribution for the playoffs. So let's swap this in. That right there and right there, and let's see just how much lower this is. It's about 50%. It's crazy. So yeah, again, these rotations are getting a lot shorter in the playoffs, which is not a surprise. And then we can also take a look at the other stats here. I think this should be a pretty simple swap in our function. So if we want to look at just points here, I think if we just change that out for points, can rerun this, and we'll probably have to switch our bin end as well. But let's just see. So there's our distribution. This goes up to 38. We can keep the size of 1. So 38. 38. Okay. So again, I see a similar type of thing here. But yeah, this is most frequently here. Both distributions of similar shape at that right skew. Just the playoffs is a little bit more extreme, with even more players scoring fewer points per game, and you have more players on the tail end of this distribution scoring higher points per game. So that kind of goes to show that in the playoffs, for the most part, your stars are going to increase their averages here. So interesting stuff. And again, we can do that with any stat, but for the sake of time, we will conclude this part of the analysis. And let's move on to part 3. So how has the game changed over the past 10 years? So I also, again, want to be able to compare this from the playoffs to the regular season. And let's just start like this. So we want data dot group by, and let's group by the season start year here. And let's just get our total stats for each of the 10 given years. So we'll put in our total calls list again. Say dot sum. I think we're going to have to reset our index again to pull that index into a column. Let's see what this looks like. Okay, that all looks good. So those are our total stats for each year. And we could just go ahead and graph all these stats. Problem is here is if you look at the minutes, total minutes played here, it's going to be pretty much or pretty significantly lower in 2019, 2020 due to the pandemic. So from COVID, the NBA did lose some games there. So it's not really a fair comparison. So we want to kind of look at this again on a per minute basis. And this time, to make our stats a little bit more readable and a little bit, give them a little bit more real world meaning, I want to look at them in terms of numbers per 48 minutes played per team. So we can add some factors into our calculation to get that, which we'll do in just a second. But we can just go ahead and name this data frame here. So we'll call this change DF. And now another stat I want to bring in is total possessions. So there are two main ways we can standardize our data. One is per minute and another is per possession. What I suspect here is that not only have a lot of these stats kind of changed over the years, but the pace of play measured in possessions has also gone up. So a very true measure of how stats have changed, the truest measure will likely be per possession, or the way we'll calculate it, again, to make it more readable, is per 100 possessions. Because if you think about it, if, let's say, points, for example, if there are more possessions in the game, then teams are essentially playing faster. So they have more opportunities to score. But just because they're playing faster and taking more shots with more possessions doesn't necessarily mean they're being more efficient. So the per possession is like the ultimate measure of efficiency in the NBA. So that's what we're really going to look at. But we'll look at per 48 minutes first here. But let's pull in an estimate of number of possessions. So we don't actually have that stat, but we can get a pretty good estimate for it. Because if you think about just basketball-wise, how can a possession end? It's with, number one, a missed shot, or a made shot, I should say, a made shot or a missed shot that is rebounded by the defense. And this with no offensive rebounds. We also have turnovers in a possession. And then free throws are the other option. So we can calculate those first two pretty easily. It's free throws where it gets a little gray area. But this will still give us a pretty good idea of where we are, which is really what we need for the purpose of this analysis. So here's a formula that we're going to use. So we'll call this possessions and then est for estimated. And so it's going to be equal to, so field goal attempts minus our offensive rebounds plus turnovers, and then plus free throws. But not every free throw ends the possession. So we have to kind of think about the way we're going to do this. So plus free throw attempts. And so you could say, okay, so most times a player is going to the line, they're shooting 2. So you could say 50% of free throws, and that would make pretty logical sense. The issue here, though, is that you also have some, you can almost call them outliers, but in the case of an and one, or a player fouled shooting a 3, or technical free throws, that this assumption doesn't fully hold. So most calculations that I see, I think there are other ways to do this, but the simple and common formula here is to use about 44% of free throw attempts. So this is where you get a little bit of estimating going on. The other bit of gray area we have here is these are player stats, not team stats. And there are ways, I believe, you can correct me if I'm wrong in the comments, but there are ways to accumulate team rebounds and team turnovers that are not assigned to a player. So I think shot clock violations, for example, are only team turnovers, and obviously they end the possession. They're not assigned to any given player, though. And then for offensive rebounds, for example, if a rebound is deflected out of bounds off of the defense, I think that is a team offensive rebound, not an individual. So there can be a little variability here, but again, this should be good enough for our purposes, and that's really all we need. So let's go ahead and run this. And now we should have our possessions estimated. I want to pull this column over to the left. It'll make it a little easier when we run a for loop. So we can kind of slice this data frame here. So we want list so change df.columns, and let's just get the first two. So we'll keep season start year and minutes in place. And then let's add the possessions column, and then plus the rest of the columns, excluding possessions estimated. We don't want to double count that column here. So let's copy paste this over to make it easier. And so now we want to start at index 2 and end before our last column. So before -1. And let's see, make sure this runs. That looks good. And so we can overwrite our change df. Okay. And now, since we just did a group by here and took our totals, we lost our ratios. So we want to recalculate all of those. And it's going to be similar to what we did above. So change df, field goal percentage equals field goal makes divided by field goal attempts, and so on. This is going to be the same ratios we calculated above. I will go ahead and skip ahead until I have those all typed in. Okay, so we have our ratios in, and now let's just go ahead and print out our data frame. So there are all of our ratios. And now we want to make this on a per minute basis, but let's create a new data frame. So this will give us a bit of a checkpoint so we can go back and change up our analysis later. So let's say we'll call this change per 48 df. That equals change df dot copy. And now, so for our for loop, let's make sure we get the right indices for our total column. So we don't want to divide our ratio columns over here by minutes. So we can go ahead and run that. Then let's just see. Let's get our columns here. So we want to start with possessions. So that's index 0, 1, and 2. So 2, and then let's guess like about 20. And I think points is our last one. Yeah, so this is going to be at index 18 there. So we can cut that and we'll put it into our for loop. So for column in columns from index 2, stopping before 18, then same thing as above, we're just going to overwrite these columns. So column equals column slash minutes. But this time, so this calculation here is just going to give us the average stats per minute per player. So we want it per 48 minutes, and we also want it per team. So we can change up our factor here and multiply it and put that in parentheses. So we want per 48 minutes and then per team. So there are 5 players on the court at any given time for a single team. So 48 times 5. And let's go ahead and print this out and make sure that this runs smoothly. Okay. And so these are going to be all of our average stats for the entire season here per 48 minutes on a given team. So if we just look at something like points here, so scoring, you can tell, has gone up over the years. We have other stuff like, I would assume that some shooting numbers also have gone up. So definitely 3-pointers. This is probably going to be our most notable change, is the explosion of the 3-pointer in the NBA. You also see that possessions per game have gone up as well. So the pace of play is increasing. And in a second, we're going to do the same analysis, but per 100 possessions instead. And that'll be just kind of the truest measure of change because we have it scaled per possession. So let's go ahead and actually, we can just graph this and just get a look at a few of our traces here. And I think we can drop minutes. So let's go ahead and do that. So this column is no longer needed. So and let's graph it. So we want to add a trace for each one of these columns here. So each column will be on the y-axis, and then our season start year will be in the x-axis. And because we have this in an integer form, Plotly, which we're going to use, obviously, will automatically sort the axis for us. So we can create a for loop here. So we can say for call in change 48df dot columns. And now that we dropped minutes, this is going to be from index 1 and on. Let's specify our figure as well. So fig equals go dot figure, capital F there. And then we'll say fig dot add trace. So adding a trace for each column through our loop here. And then we're going to want to scatter. So it's going to go dot scatter. It's technically really going to be a line plot, but we'll see in a second. Then on the X, we want the year here. So change for 48 df season start year. And then on the Y, we're going to want the column. And then let's name our traces as well so we know which one is which, and that's just going to be equal to the iteration of the column. I think that should be all we need. So let's go ahead and show our figure. Okay, and a beautiful thing about Plotly here is because you can see this is pretty cluttered, tough to read. We can just go ahead and hide these traces we don't want. So let's say we just want to show possessions per 48 minutes. Just go through and hide all of these. Just clicking through. We can have our ratios down here. And here's your graph of possessions per 48 estimated. Let's take a look at, let's look at 3-point attempts. So massive increase, pretty crazy, just how much this has increased and how much the game has changed, moving towards that kind of Mori ball model of taking a lot of threes and layups and minimizing those inefficient mid-range shots. We can also kind of look at, let's see how offensive efficiency has improved. So true shooting is also up pretty significantly. So we have about 53 up to 56 in this most recent season. Let's look at some of our other ratios here. Just scoring in general actually is also up. But again, this is per 48. When we scale to per 100 possessions, this may or may not change. But we'll see about that in a second. So field goal percentage is up a little bit, but not quite as high. But interesting though is you have teams shooting more threes and increasing their raw field goal percentage. Just very slight change there, just about 1%, give or take. So this is assist percentage. This, you could kind of look at this as a measure almost of like how much isolation ball our team's playing. So that's going to be percentage of field goals that are assisted. So we got about 59% up to 60. Yeah, so not a whole lot of a change there. We can look at more of these when we get our change per 100 possessions graph. So let's go ahead and copy this. And now we want to adapt this for a per possession basis here. So we'll call this change per 100 df. And again, we're basing it off of starting with our change df.copy there. And I think, let's comment this out for now. Just want to make sure our column indices here are correct. So this time we want to start with our index right here. So on field goal make, so that's going to be 0, 1, 2, and 3. So let's change this to a 3. And for now, let's comment out our graph. We can get back to that in a second. And I'm going to go ahead and swap out each instance of change per 48 df with change per 100 df and skip ahead to when I'm done. Okay, so we have our data frames all swapped here, 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 and everything. We have that index changed to 3. We also want to swap out minutes for possessions here, and then our ratios we want per 100 possessions, just times 100 there. And then also we want to drop both minutes and possessions estimated so that we can start again from index 1 when we go to graph this. And this is our result here. So we just have our year and then all of these stats per 100 possessions here. So just take a look at a few of these. You can see that when we take into account the increase in pace of play over the years, some of these stats actually really haven't risen at all, and some of them actually declined. So we look at something like field goal makes. So offensive efficiency hasn't gone up that much. If we look at, let's get points. So okay, so scoring has come up a little bit. I think that's mostly going to be due to the three-pointer as well as free throws. I mean, let's look at free throws. Okay, interesting. So free throw makes are actually down. Same with attempts. And I think that's kind of interesting. I think there's a bit of a narrative in the NBA that it's become just a foul drawing league of guys just jumping into each other or swiping through guys' arms. But if you look at free throws per possession here, they're down, as well as, let's see, fouls. So fouls are down as well. So the extra scoring, the extra offensive efficiency is really not coming from free throws at all. It's actually, I think, coming for the most part due to the three-pointer here. So a ton more attempted and made. Let's look at our percentages. So this is percentage of field goal attempts that are threes. It's gone up, wow, just 24 all the way up to 40. It's just incredible change. Shooting efficiency up a little bit. And let's see what else we can look at. True shooting also up. So let's go ahead and graph this. So we can uncomment this out. Again, I just switched out data frame here. And because we dropped these two columns instead of just one, we can keep our same index here in the for loop. So let's go ahead and run that. And so first, I just want to show, let's look at fouls. I think that's one of the most interesting ones. I think a lot of people know about the three-pointer, but again, I think that this is just a very common narrative out there that the NBA is just about guys jumping into defenders and drawing fouls. But this kind of counters that argument here. It's very interesting. So fouls per 100 possession down, and then we have, let's see what else. Let's look at free throws again. Get free throw percentage actually. So that's going to be the ratio of free throws to attempts. So this is actually up a little bit, interestingly. Not by a whole lot. Let's look at field goal attempts. So attempts are also up per possession. So I think that should indicate, let's look at rebounding. So offensive rebounds are down. I think that could be an indicator of pace of play. So more teams are concerned about fast breaks. So sending fewer guys to the boards and more guys to get back on defense. That would be my guess there. Defense or rebounding is up. Again, those two should be negatively correlated because the more offensive rebounds you have, naturally that means the fewer rebounds the defense will be grabbing. Total rebounds. Don't think there should be a whole lot of change there. Yep, that makes sense. Field goal percentage is maintained. Yeah, been pretty static. So there aren't going to be that many more rebounds available. So those two should be strongly correlated. And let's look at scoring. So scoring, again, efficiency is up. So points per 100 possession is up. And I would mostly attribute that to the change in the way the game is played in terms of three-pointers. So again, when you recreate this code here, you can go through and look at all these different traces. Again, Plotly makes it super easy to just graph all of these and then show and hide what you want to see. And I think you just double click to bring it all back to normal. So, okay, let's move on to, I want to compare now, create a new little subsection here. Let's compare the regular season to the playoffs. So we already kind of have the code here. We're just going to kind of adapt it to the regular season and the playoffs. So if we go back up to our initial group by up here, all we have to do is swap out data here for our RSDF and our playoffs DF. So for our comparison analysis, let's only look at per 100 possessions. So we're not going to go back and look at per 48 minutes again. So again, I think per 100 possessions is just the best metric to compare because again, it's taking the change in pace of play into account as well. So here's how we'll do that. So let's call this first. We'll call this RS change DF. This will be RS df.groupby. I think everything else should remain the same. Let's print this out, make sure. That looks good. Then we can just copy paste this and make this one a playoffs change DF and swap out our data frame here as well. Okay, and now let's create our columns here. So we need possessions and let's put this into a for loop actually. This will make it quick. So we can just say for I in, then we want our two data frames. So our SDF and our playoffs change DF. So I, then we need possessions estimated. And that's going to be equal to, again, field goal attempts minus offensive rebounds, oops, plus turnovers, and then plus 44% of free throw attempts. Let's create a possessions per 48 here so we can compare pace of play as well. So we'll do I and then possessions per 48. And that will be equal to, we want this column here. And then we'll divide that by minutes and multiply this by 48. Now let's just pull in all of our ratios here. So it's going to be the same thing as everything we did. Where is it? Everything up here. I'll go ahead and pull that in and skip ahead to when I have it in the for loop. So we have all of our ratios in, And now we can just keep this for loop going here. And I want to add in, just overwrite all of these total columns with the totals per 100 possessions. So now we can just add a nested for loop in here. So we'll say for call in our total calls. And that equal to, so again, we'll just overwrite this. So I, again, still refers to the data frame. So I column equals I column slash I want possessions estimated and multiplied by 100. So then let's go ahead and print these out. I think this should be good to go. Let's see. I'm going to have to drop a couple columns as well, but we'll see. So rs change df. Okay, so this looks good. And so what we want to drop here is, let's see. We can drop our possessions estimate, and then let's see what else we're going to drop. Actually, I think we want to multiply this by 5 here. We forgot that. Let's see. We can always rerun this loop again. That number seemed a little low. Okay, possession per 48. That looks much better. And now let's drop these columns. So I think we can even, yeah, we can say in our for loop even. So let's go back in here. Not in this part of the for loop. We just want the part where we're passing through our data frame. So we can say I dot drop columns equals, and then we want to get rid of, I think, minutes, not telling us much, and we can get rid of estimated possessions. I think that should be all we need, but we'll make this in place and then print out our data frame again. And now let's just check our playoffs, change df. So now what we have here, this all looks good, is we have 2 identical data frames. So same exact structure, same season start year order and everything, same columns. So what we can do is we can just divide these columns by each other and create kind of a percentage change, because again, we have this wouldn't work if we didn't have the same exact data frame structure. So that's why our for loop here was so nice. And so what we can do is we can say, let's look at the percentage change from regular season to the playoffs in each year. So we're going to see which of these stats have been going up, which go down in the playoffs. So our formula here is going to be just a normal percent change. So our baseline is going to be the RS change DF. So playoffs minus regular season divided by regular season. That should give us a percentage change here. I'll make this a little more readable. Let's multiply this by 100, and I think we can round this as well. And we'll deal with our season start year in a second. But this looks good, so let's round it. Say round that to 2 decimal places. Maybe we can do 3. We'll go to 3. Okay, so we have all of our percentage changes. And let's assign this to a new data frame. So we'll say comp for comparison. So comparison change df equals that. And now let's take care of our season start year. So we already know what these are. This is 2012 all the way to 2021. So we can just almost kind of hard code this in. So season start year, and that equals list range from 2012 and then stopping before 2022. And let's print this out again just to make sure. Okay, so we have all of our years in. And now we can go ahead and graph this. So let's pull in our code from the graph up above. And then swap out our data frame. And that index from 1 on is good because we're starting here at field goal makes. And before we run this, let's just get a look at which of our stats are going up and down so we can get an idea of what we want to hide and what we want to show with all these traces. It'll be a bit cluttered at the beginning. So again, remember, this is from regular season 2 playoffs. So an increase of 10.5% here. That means it's higher in the playoffs than it is in the regular season. So we see, again, there are more free throw attempts in the playoffs. We got more free throw makes. Let's see what else. Rebounding doesn't look like it changes much. Assists are down, so maybe more ISO ball. Steals down as well, so I'm guessing turnovers probably down for the most part, except for this last year, interestingly. And fouls are way up. Very interesting. So more fouls, more free throws. Let's look at pace here. So the game is slowing down. Interesting. More grinded out. I guess that kind of aligns with the playoff stereotype. And let's look at some of these ratios here. So more 3-pointers in the playoffs. Shooting efficiency, points per attempt, look about steady there. Again, more 3-pointers. Free throw rate is up. True shooting looks about level. So very interesting. Let's go ahead and run our graph. Okay, let's take a look at, let's see. I'll just look at possessions per 48 first, and let me just pause and skip ahead. Okay, so here's our graph here. And unlike last time, we're not going to be looking at almost like you'd say like the slope or the rate of change. We need to look at this relative to 0 here. So notice that all but one of these years, the change is negative. So that means that the pace of play has been slower in the playoffs than it is in the regular season. So just a important note on reading our graph. Let's look at scoring here too. Yeah, so scoring efficiency, remember, so this is points per 100 possession. So efficiency hasn't really changed all that much. You see it's up and below 0, depending on the year. So not a whole lot of change there. Look at fouls. I think this one was up pretty significantly. So even at the bottom here, up 6%, pretty incredible. All the way up to like 14% here, almost 13% in 2021. So interesting, more fouls in the playoffs. I feel like the stereotype is almost that referees are going to swallow their whistles in the playoffs, but not the case when you actually look at the data here. Look at turnovers. Turnovers are down except for this past year. Kind of strange. You could equate that to maybe higher level of play in the playoffs. I don't think blocks changed much. Yeah, looks about hovered around 0 there. Look at assists. Assists are down again. So I know we have that narrative in the playoffs that like you need guys who are going to create their own shot. And I guess this is evidence toward that. You can look at assist percentage as well and see if that holds up. So assist percentage also down for the most part. We had a couple of years where it crept back up to 0. But again, assist percentage is percentage of field goal makes that are assisted. And see if free throw percentage changes because this can indicate some pressure. Looks like not. So for the most part, it's going to be around 0 there. So NBA players are going to be pretty good shooting free throws regardless of the situation. That's kind of what the numbers tell us. And then let's look at one last thing here. I think 3-pointers was very interesting. This is just field goal makes. Field goal makes are down per 100 possessions, but again, free throws are up, so that kind of compensates in terms of overall offensive efficiency. And let's look at 3-pointers. So 3-pointers made is way up. Got up over 10% here in some years. So I'm assuming attempts should be up too. Yep, pretty significantly there. And then we'll look at percentage of attempts from 3. Again, positive every year, percent change in the playoffs. You can just go ahead and reset that. And that concludes our analysis for today. So again, if you have more ideas or anything else you want me to take a look at with some NBA stats, you can go ahead and leave that in the comments. And please leave a like if you enjoyed the video and you thought this was interesting. It really helps grow this channel, so I'd really appreciate if you leave a like and subscribe to the channel for more data analysis content in the future going forward. Thanks for watching.